Hi folks, today we're going to learn how to analyze lines of fit. In the last section, 4.4, we learned how to draw a line of fit on a scatter plot to identify trends. And we're going to look at those a bit more analytically and also come up with a better line of fit called a line of best fit using technology. So first, let's look at how to evaluate lines of fit like we did at the end of the last section. We're going to look at these data here that were from the last problem we did in section 4.4 part C, and I'll scroll back up to that in a moment. But basically, we plotted some data and we came up with this line of fit, this equation, y equals 10x plus 6. And we want to know, is that equation a good fit for our data? And we're going to go about looking at that by calculating residuals. And residuals are the difference of the y value of a data point and the corresponding y value found using the line of fit. So first, let's scroll back up and see what we did here. This was a relationship between millions of subscribers to a particular website in the years since 2010. And so, our line looks like it's a good fit, but of course, we want to be quantitative in our analysis. We don't want to just say it looks good. We want to have like a number that we can put on the value. And the first step towards doing this is looking at residuals. And the residuals are basically going to look at how far our points are above the line of best fit or how far our points are below the line of fit. So what we need to do first is calculate our y value from the model. So we're plugging x values into this equation that we came up with. So here our x value is 0, so we do 10 times 0 plus 6, and that equals 6. And we continue the pattern going down the list, getting our various y values. So here we would do 10 times 6 plus 6 is going to equal 66. 10 times 7 plus 6 is going to equal 76. And 10 times 8 plus 6 is going to equal 76. So we now have the y value that our model predicts for each of our input x values. Now the residual is going to be the actual y value minus the y value that we calculated from the model. So we're going to do 9 minus 6, and that gives us 3. We're going to always subtract in that order, the true y value minus the model y value, because the positives and the negatives are going to be important. So I've done the first 3 here, but just continuing the pattern, here I have 33 minus 36, which is negative 3. I have 43 minus 46, which is also negative 3. I have 53 minus 56, which is also negative 3. Then 71 minus 66, which is 5. And 76 minus 76, which is 0. And then 89 minus 86, which is positive 3. So now I have a set of residuals here, and you can see that sometimes my equation is below the original true value, and sometimes my y value from the model is above the original y value. And if we plot these data using the information using 0 as my x and 3 as my y, or 1 as my x and 5 as my y, this graph here shows us what this graph of residuals looks like. So here I've graphed the first 7 points, but I haven't graphed these last 3, so I'll go ahead and add those in now, just to be clear on where I'm getting the numbers from. The x value is 6, the y value is 5, so I'll draw a point here. And then when the x value is 7, the y value is 0, so I'll draw a point here. And then when the x value is 8, the y value is 3, so I'll draw a point here. By graphically analyzing the residuals, we can gauge how good a fit our model was for our data by seeing if, there are a few things that we check for. First of all, we want to make sure that the absolute values of these residuals are all relatively small. Here, the biggest residual is 5, and so these are all quite small residuals given the values of our data. Another thing we want to check for is, are the points reasonably evenly distributed above and below the x-axis? And so here we've got 4 points above, 3 points below, and then 2 points on the x-axis. So this is reasonably evenly distributed. And also the points should be distributed fairly randomly. There shouldn't really be a pattern here in the distribution. And all of these things appear to be true here. So we would say that yes, the model is a good fit. And the reason for this is because the residuals are all small. The absolute values of the residuals are all small. The points are distributed reasonably equally above and below the x-axis, and they are distributed randomly. There doesn't seem to be a specific pattern of which points are above and which points are below the x-axis. So let's look at an example that maybe isn't a good fit, a model that isn't a good fit for the data. So this table shows ages X and salaries Y and thousands of dollars of 8 employees at a company. This equation was used, 0.2x plus 38, to model the data, and then we're being asked, is that model a good fit? Again, we can use residuals to analyze this situation, but to calculate the residuals, I first need to calculate the y value from the model. So where did I get this 45 from? I took my x value, which was 35, and plugged it into the equation. 0.2 times 35 plus 38 gives that number 45. So the first 5 y values from the model are given here for you. I'm going to go ahead and calculate the last 3. So I'm going to do 0.2 times 47 plus 38 is going to equal 47.4. 53 plugged into the equation is going to give 48.6. And 55 plugged into the equation is going to give 49.0. So now I know the predictions that my model gives, and I can compare those predictions with the y values of my original data points. So if I do the subtraction now, the true y value from the y value from minus the y value from the model, 42 minus 45 is -3. And then moving down the list, 44 minus 45.4 is -1.4. And I just continue the list here to calculate all of my residuals. 0.8. 50 minus 46.6 is 3.4. 52 minus 47.0 is 5.0. 51 minus 47.4 equals 3.6. 49 minus 48.6 is 0.4. And 45 minus 49.0 is negative 4.0. I've graphed most of these points, but the last three still need to be graphed. So just as a reminder of what values to use. So if I use this value of x with this value for y, the residuals is what I'm trying to graph here, then I would have a point, let's see, 47 is about here, and 3.6 is about here. No, 47 is a little closer this way. Then at 53 and 0.4 would be around here. And then 55 negative 4.0 would be about here. When we look at this graph, there seem to be, well, maybe approximately the same number of points above and below the line. I don't know, 5 above and 3 below, so it's a little bit lopsided. Although this one's quite close to the line. And also, all of the residuals are quite small in size. Again, 5 is the largest residual that we have here. However, there seems to be a definite pattern. The line kind of goes up in, kind of goes from negative to positive in residuals, and then kind of goes back down. So there appears to be a pattern here. Whenever any of those 3 checks are false, then the line is not a good fit. So in this case, the absolute values were relatively small. The points were distributed above and below the axis approximately equally. That was kind of ish true, but the points were definitely not distributed randomly. And so that's what we will say here, that this is not a good fit. And it's not a good fit because it has a kind of upside down U shaped pattern. And what a pattern means in this context, if you have a pattern to the residual graph, then that suggests that the data are not linear. All right, so this is how we would analyze a line that we had drawn by hand. Of course, with modern day technology, calculators, computers, there are better ways to do this. And so let's look at how to do this. Now, I will provide a link in the comments or in the description to a good calculator website. I will do this example on a calculator, but I'm not going to troubleshoot every possible problem. But I'll do what I can. And leave that to the calculator YouTube professionals here. So if I kind of split my screen a bit more, but I still want to see these data, these data show a relationship between the duration in minutes of the eruption of the geyser Old Faithful in Yellowstone National Park and the times in minutes between the eruptions, the time to the next eruption. So what I'm going to do here, let me just clear the screen on my calculator. Let's go here. All right. And if you want to plot a scatter plot, then you need to enter buttons in kind of the statistics function. So I click this stat button and I get a variety of information here. And I'm going to choose the edit function. So I'm going to click 1. Now, I already have data here in these lists, and I don't want these data here. I want to enter my own data. So I'm going to go up to the column heading and click clear. Now at first it looks like nothing happened, but if I click down into the body of the list, I can see that the information has in fact been cleared. I'm going to do the same thing to this list, clear, and although it looks like nothing happened, when I scroll down I see that it has been cleared. And now I'm going to enter the data that I see over here in my data table. So I'm going to type in 2.0 for the first data point, 3.7 for the next x value, 4.2. If you ever forget to do a data point, these don't have to be in any particular order. You can see that sometimes the numbers increase, sometimes the numbers decrease. What does matter is that you match the correct y value with the correct x value. So my 60 has to go with the number 2, my 83 has to go with the number 3.7. So now I have my data plugged into my graph, and if I go to the graph button, oh, it looks like I have a line there from a previous problem. So sometimes this happens as well, just like there were previous scatter plot data, there was a previous line here. So I'm just going to clear this equation away. And now my graph has some data points here. Now, my data points are kind of clustered together and a little bit hard to see, and yours may not even be visible depending on the settings of your view screen here. So if you click the window button, you can change the settings to go to set to whatever x values you want. My x values range between kind of 1 point something, and they don't go all the way up to 5, but I'm going to go ahead and go from 0 to 5. So 0 up to 5, and I can keep my markings every 1 unit. And in the y direction, I'd like to keep the x-axis in here, so I am going to start my y-axis at 0. But my max value kind of goes up to, if I go up to 90, that should be plenty. Oops. Starting at 0, going to 90, and markings every 5 units seems reasonable. So now when I look at my graph, I can see those data points a little bit more clearly. They're not all clustered together on top of each other. So I've plotted the data points, but I also want to have a line of best fit. This is different to what we did in the last module where it was just a line of fit. This is going to be a line of best fit where an algorithm is going to minimize those residuals that we just calculated. And of course the calculator or computer can do that much better than me. So how do I know what the equation for the line of best fit is? Well, if I go back to that statistics menu, there isn't just this edit menu, there's also this calculation menu if you click over to the right here. And under the calculation menu, there is a linear regression option, option number 4. So you can either type the number 4 or scroll down until you see, until it's highlighted and hit enter. And it will ask you to confirm that you want to use list number 1 and list number 2, back from when we first entered these, edited the statistics lists. And those are correct, so I want to just go on down into calculate. And when I calculate, you should see an a value, a b value, an r squared value, and an r value. Now, for this activity, the r squared value isn't so important for this. I'm going to go ahead and put down 11.99 was the slope. Notice it says y equals ax plus b. So a is the slope variable. So the slope is 11.99 and the b value, the y-intercept, is 35.12 and my r value is 0.9787. And that's probably too many sig figs. So I'll go ahead and just say It doesn't matter for the purposes of this problem when we see what the R value gives us. But those are kind of the three important things that I need you to look at in our class. I should mention that if you don't see an R value here, there's probably a particular feature of your graph that's not turned on. So let me show you how to turn that on. If you access the catalog, which is the blue feature above the 0 button, it's a blue feature, so I access it by doing second and then 0. So that gives us the catalog. And then you scroll down until you get to the D section. When you get to the D's, there is a diagnostic feature, diagnostic on, and you want to make sure that it is turned on by hitting enter and then hitting enter again. And when you get that done feature, then that turns the diagnostic feature on, and you should see an R value for your line of best fit. Incidentally, this can also be a reason that you might not see data points when you graph your scatter plot. While I'm at it, there's one other reason that you might not see data points when you plot your scatter plot, and that's to do with the stat plot feature, which is above the y equals button in the top left corner. So if I click second and then the y equals button, you can see here that there's an option to turn the statistics plots on and off. So plot 1 is on, but plot 2, plot 3 are off. I entered my data under plot 1, and so if this option 1 said off, then what I could do is select it and enter it, and then I would have the ability to toggle this on or off. Of course, I want it on, so I'll leave it on, and then when I go to the graph, I do see my data points. All right, I have the information I need for my line of best fit, which I recorded over here on my notes sheet. How do I show that on my graphing calculator? Well, if I want to graph a line, this is just a normal y equals feature. So I'm going to click the y equals button in the top left corner, and I'm going to plug in the equation for a line using that slope and that y-intercept that the calculator gave me from analyzing the line of best fit. So I'm going to type in 11.99x, and you can choose the x button up here next to alpha, and plus 35.12. And now when I go to my graph, I do see that line of best fit incorporated on top of my scatter plot. Moving back to our data here. We use technology to find an equation of the line of best fit. The equation for our line of best fit was 11.99x plus 35.12. And we graphed the equation with the data, and we saw a graph that looked similar to this. Next, we're asked to identify and interpret the correlation coefficient. The correlation coefficient is this R value here. And scrolling back up so you can see our definition for correlation coefficient. The correlation coefficient is a number between -1 and +1 that tells how closely the equation of the line of best fit models the data. And if you look at this line here, you can see that when R equals -1, there's a strong negative correlation. That means the graph has a downward, a negative slope, and the data are clustered really close to the line. A strong positive correlation, it would be when an R value is close to 1, and that means that our line has a positive slope. And it doesn't have to be a steep slope. I'm going to draw this more shallow this time. But what it means is that the data are clustered really close to the line. The closer the R value is to 0, the more that means that there's no correlation between the X and Y values. That there's not a linear relationship. So coming down here to look at our correlation coefficient for this example, the R value is very close to 1, so this is a good fit. This is a strong correlation. And not only is it a strong correlation, it's a strong positive correlation. So we know that the slope has a positive slope, which of course we knew already from our calculation. Looking at the last question, interpret the slope and y-intercept of the line of best fit. So the slope, remember, of your line of best fit is, slope is the y value over the x value, the change in the y value over the change in the x value. So when we look at slope, we look at the units in the y direction divided by the units in the x direction to help us interpret it, the meaning. So what this means is that there's 11.99 minutes of wait time until the next eruption for every 1 minute of eruption. Basically what we're saying is that the longer Old Faithful erupts, the longer you have to wait for the next eruption. So if there's a really major eruption, you're having to wait longer for the next one to happen. So that's the interpretation of the slope. Let's look at the interpretation of the y-intercept, which is 35.12. The y-intercept focuses on the units in the y direction. So this is a 35.12 minutes of wait time as kind of your minimum. No matter how small the eruption is, the wait time is always at least 35.12 minutes. At a minimum. Okay. So that's kind of a real world interpretation of the slope and the y-intercept for this particular example. How do we use this information to help us make predictions? There are two kinds of predictions you can be asked to make. You can be asked to interpolate data or extrapolate data. And they're very similar. They're certainly similar in the math that you do with them, but they do have slightly different meanings. So if I wanted to approximate the time until the next eruption after an eruption lasting 3.5 minutes, if you look at the graph here, 3.5 minutes falls in here. Okay. And that's within my data range. I'm between data points that I already know about. This is called interpolation. I'm going between data points I already have. Just like an interstate highway goes between states, interpolating goes between data points we already know. The way you interpolate is you just take your equation, which in this case, remember, is y equals 11.99x plus 35.12. And we plug in the x value of interest to us. So I'm going to say 11.99, and I'm going to plug in the 3.5 plus 35.12. Calculating this out, plugging it into your calculator, you get 77.085 minutes of wait time. And that's all you need to do. Now, is this interpolation or extrapolation? We've already said that this is interpolation, and it turns out that interpolation is more accurate than extrapolation because you have certain data points on either side of the value that you're investigating. You can just be more sure that the pattern that you've identified, in this case linear, does hold true for that value that you're investigating. So this is more accurate. If instead we look at an eruption that we're asking to predict the wait time after an eruption of 5 minutes, scrolling back up to here, we can see that 5 minutes is beyond the data points that we've collected. So we can still use our line of best fit to calculate, to kind of estimate this value, but it is less certain because we don't have more data on the other side of that 5-minute mark. We can't be sure that our data stay linear the whole time. So, scrolling back down, we just do the same exercise where we use our equation for our line of best fit, and then we plug in this 5 value for x. 11.99 times 5 plus 35.12 works out to be 95.07 minutes. And because this is extrapolation, this is less accurate. It's still a reasonable guess, we hope, if our line of best fit holds true, but it is less accurate than interpolation. I almost forgot. There was one other thing I wanted to show you about how you could go about getting this information using your graphing calculator rather than plugging the value into the equation. So if I go back to my graphing calculator screen here, then you can use the trace feature on your graph to find different data points. Now, at first, you can see that my cursor is kind of hopping around as I toggle through the different data points, because you can see up here in the top left corner it says plot 1. It's doing my scatter plot. It's tracing my scatter plot. If I click the up or down arrow, though, I'll switch to my linear equation, y equals 11.99x plus 35.12. And if I trace here, I can scroll to where the x value equals 3.5, or I can at least get close to it. It looks like I can't get exactly on it. I'm at 3.4848 or 3.52. But you can see here that the y value is approximately 76.9 or 77.3. And if I scroll up to where the second question that was asked was about the time point 5 minutes right there, and I get that my y value at 5 minutes is exactly 95.07. So I can look up those pieces of information using the trace feature on my graphing calculator. The last thing that we need to think about when we're looking at these scatter plots and analyzing scatter plots is whether a relationship is just a correlation or whether there's actually a causation in the relationship. And really what we're asking ourselves here is, does the independent variable x cause the change that we see in the dependent variable y? You can have correlation without causation, but if there is causation, then there has to be correlation. So, say whether a correlation is likely in the situations outlined below, and if so, say whether it's a cause-effect relationship or just a correlation. So, does time spent exercising affect the number of calories burned? Yes, the more time you spend exercising, the more calories you burn. That's a positive correlation. Okay. This is also a causal relationship, because the more time you exercise, more exercise causes more calories to be burned. Okay. In the next example, the number of banks in the population of a city. Is there a correlation there? Well, it's true that you're likely to find more banks in a big city that has a lot of people. So there could be a positive correlation there, maybe. But this is definitely not a causal relationship. If you have more banks, that does not cause the population of a city to increase. So not causal. More banks does not cause population to increase. So even though there is probably a positive correlation between these two things, it's not a causal relationship. I hope this helped.